So yeah, welcome to the ELIXIR webinar. I will today talk about Bioconda and Biocontainers from the perspective of tool deployment and sustainability in science. So actually, if we have developed tools, how we get them to the user, how we deploy them in various settings. So the cloud topic or the HPC gets more and more important. And the question is, how can we get our tools in a reproducible way to scientists so that they can use it? So tool deployment and sustainability in science is more or less like I have drawn it here. So you start with a question, you have a chunk of code, you develop a chunk of code, and in the end you want to deploy it either on your computer, on the computer of the scientist, in HPC, in cloud computing. This doesn't matter, but you need to execute your code in some environment. The question is, how do you get your program into the execution environment? If you Google what a package manager is, a package manager should more or less be in charge of finding, installing, maintaining, or even uninstalling software packages upon the user's command or user's request. So this talk will more or less talk about the packaging of software. And this sounds a little bit crazy in the year 2017 that we still need to cover this topic because packaging or software packaging is as old as software development. So if you follow the history of computer science, every developed software needs to be deployed on different architectures. So back in times in the 70s and 80s, it was just your code, which was more or less sent around or transferred, and then you need to compile it by yourself. So you are more or less the package manager at that time. Yeah, but over time, there have evolved many packaging techniques, especially in the Linux or Unix field. They invented in the early 90s the package manager like apt-get from the Debian system or from Red Hat systems, the Yum package manager that were kind of bound to an operating system and where only root or if you have super user privileges could install packages. In the scientific field, more or less every programming language, be it R or Python or Perl, had its own package manager. So many of you are probably familiar with CPAN or CRAN or pip or setup tools from Python. All these are kind of package managers that tries to get your specific Python or Perl code onto your computer. They try to be smart in handling dependencies and so on, depending on the package manager, they do a good job or not. But all these package managers are kind of bound to a programming language, whereas the distribution package managers are bound to an operating system. So whatever you choose, you don't have a universal package manager that you can, where you simply can assume, okay, a user can install a specific package on a variety of operating systems, no matter which programming language you use, and so on. Recently, there was the container technology introduced in the Linux kernel, and projects like Docker or Rocket have more or less or are advertising a new concept of putting everything in a so-called container and then shipping the container. So it's kind of a package manager, just that the package now comes in an entire container and is redistributable. So more or less a new package manager that is able to run on OS X, Windows, or Linux, so it's not operating system specific, and it's also not bound to any programming language. The disadvantage of Docker or container technologies is that not everyone can use it nowadays. So especially HPC environments have their problems to deploy Docker containers. So it's not everyone's favorite currently, and we need to have a solution that fits more or less to all. Also, the current technology of how to create containers can be quite cumbersome and will result in packages that are way above 100 megabytes in size, which is also suboptimal. So what we actually need from a package manager is we want to have a package manager that is programming language agnostic, that is operating system independent. We want to install our packages without root privileges, so every user should be able to install their own packages. They should be able to maintain their packages, and they also should be able to manage multiple versions of one and the same software. So I want to be able to install CentOOLs in version 0.1.90, and I want to install CentOOLs in version 1.4, which was released yesterday. So, and this is needed for scientific research because this enables reproducibility. As soon as we can install multiple versions of R with different packages and can reproduce an entire workflow, this is reproducible and sustainable research. So we need a package manager that is capable of that. In addition, this package manager should be able to also install packages on HPC environments. And HPC environments are kind of special because they are usually based on a very stable but old operating system like Scientific Linux 6, or I know, for example, a few people that still running Scientific Linux 5. So they're quite old, quite stable, and they power an entire high-performance cluster. So we need to be able to get these packages on these infrastructures as well, but also we want to have it in cloud computing. So essentially, if we create a package, we want to deploy it on all different kind of infrastructures. I think a special requirement for a bioinformatics package manager is also that it needs to be easy to maintain. We have a huge turnaround in packages in bioinformatics. This means that new versions of one software is frequently released. We have a huge turnaround for one of the same package, but also one tool is replaced very fast by a new tool or a successor tool. If you remind yourself on all RNA-seq pipelines based on TopHat and cufflinks, which are more or less now replaced with star or HiSet and DESEC. So we need to deliver and we need to maintain these packages in a fast and accurate manner. So we cannot spend time and days in developing one package. So there needs to be a fast and easy to maintain mechanism, which allows us to create these packages. And the solution I want to propose today is called the Conda Package Manager, that is developed by Continuum. So that's a company based in Texas, if I recall correctly. And especially the Bioconda community that uses the Conda Package Manager to create scientific software packages for everyone. So Conda is an open source package manager. It is independent of any programming language, and it's more or less fulfills all requirements we have so far. It is fast, it is robust, and it's easy to create such packages. Installing works like any other package manager, so you just type in Conda install, for example, DeepTools, and you will get the Python package DeepTools with all its C dependencies and NumPy installed on your system in a virtual environment. And because it's a virtual environment in your home directory, you can install it, everyone can install it on their own. And you can have multiple versions, for example, of DeepTools as well. So how does a package definition look like? So because I said that we want to have a very easy definition or a very easy language to write such recipes, Conda fulfills that in a sense of it's more or less a meta YAML file which you need to refine. So you have your package definition, you just define the name of your package and the version, and then you can define a URL where you download the tarball. You can specify a checksum so that the download is verified. And then, more or less, what you need to do is you need to define build and runtime requirements. So, build requirements are, for example, GCC or CMake or setup tools. So this is the requirements which you need to build actually the package to compile them. Runtime dependencies are the dependencies if the user is installing the package, which tools do you need or do the package manager needs to install as well. So essentially, if you install deep tools, you will not get setup tools or GCC. You will get the precompiled deep tools package binaries. You will get a Python version and different dependencies what you need. And that's essentially all what is required to define a Conda package. Additionally, and what we highly recommend is to include also test cases. So as soon as this package is created, you can just try to import deep tools in your Python environment. So this is done automatically by Conda during the build process. So you just do imports, deep tools, and if Conda can import this module, everything is fine, test passes. Or you can simply run a comment, for example. So this is a binary that is available in deep tools. So you just call it bam compare -- version. If this succeeds and returns an error code of 0, everything is fine. Your package passes the tests and you are done. Also, you can define something like metadata. So, for example, you can reference the upstream development repository. You can specify the license, a short summary, and with the registry project of ELIXIR, we are even discussing to include more metadata in such a Conda package, so that the ELIXIR registry can actually query such packages, extract metadata, and annotate their own tools which they have in the registry. So a lot is possible in such YAML files, and I hope that it's easy enough to write such files without learning an additional language with just specifying dependencies. Just as a side remark, all these dependencies are already in Conda and needs to be their own packages as well. So, and then there is just an additional file that is called build.sh, and both files, the metadata YAML file and the build.sh file, are more or less the only files which you need to create a Conda package. And the build.sh file looks, in this example, for a Python package simply as that. So you have just the command python setup.py install, and yeah, that's enough to compile your first Conda package. Conda also supports something like skeleton generators. So as soon as your software project is already available on PyPy, on CPAN, on CRAN, on Bioconda, Conda can create such a meta.yaml file and a bash sh script automatically for you. So it's more or less a template, which I would say works in 90% of all cases. So that's pretty good. So what happens is more or less you extract the metadata that is already annotated on PyPy or CPAN or CRAN. We extract these metadata and create such a YAML file out of it. Yeah. And then the next step is really simple. So to build a package, you just execute conda build, and then the path to your meta.yaml file and your build.sh file, and that's it. So Conda will then automatically fetch the build time dependencies, will build your package, then the build process is finished, then it will install the runtime dependencies and test your tool in the runtime dependencies, and you are ready to go. Where it gets a little bit tricky is if you compile code. So if you compile code, you need to be compliant to a specific libc version. You need to agree on a build environment or a runtime environment. So for example, if your package hasn't defined zlib as dependency, your runtime environment needs to have zlib installed, obviously. So as a community, we need to decide decide what we assume that a runtime environment has installed. And this is where this entire community effort comes into play. To build packages that are compatible to each other, we need to agree on a common build infrastructure, we need to agree on a common runtime infrastructure, and then on specific rules to define such packages and so on. So what Johannes Köster, Ryan Dale, and the entire Bioconda community is doing is actually building a scientific community around the Conda package manager called Bioconda, where we actually set a few best practice guidelines how to develop these packages, where we now maintain specific rules for our packages, for bioconductor packages, and so on. And we also agreed with other communities like Conda Forge, for example, on a common build infrastructure. So, for example, we build now all packages on the CentOS 6 system. That means that whatever system is newer than CentOS 6 will work with Bioconda packages for sure, because this is all tested and deployed already. And this common build infrastructure and runtime infrastructure is important to share these packages and to agree on a common standard. For example, in the Bioconda community, we agreed to not assume anything on a runtime environment. So even zlib is a requirement. And we test that, so we actually have a busy box where we install the Conda packages in, test the package, and if the package is running, we say, okay, this package can now deploy to Bioconda. So we really ensure that a Bioconda package runs on BusyBox where actually nothing is installed, even zlib is not installed. If you want to build your software package on this unified build environment, we just created a script called Simulate Travis, which runs the entire compilation process or installation process in a Docker container in this unified build environment. Thanks to Ryan Dale that spent a lot of time in getting this Simulate Travis environment up and running. Yeah, and this is the way how the Bioconda community develops tools now. So we have a defined Docker container where we compile our packages. And we are joining other Conda communities. So Conda Forge is a more general purpose Conda community that maintains Perl, the main Perl package, for example, or the CMake package, or the zlib package. So all these general purpose packages, for example, the entire X server is maintained by Conda Forge, and the Bioconda community is more concentrating on bioinformatic or scientific research oriented communities with a much higher turnaround. Okay. What we have done in the last 1.5 years is we created an extensive documentation about the entire build process, but also about how to install Conda packages, how to maintain different virtual environments, how you can use this actually for your scientific and research. So this is on the website, bioconda.github.io, where you find this website. But we also include a lot of documentation for developers. So, for example, you see on this side here an extensive list on how can I integrate Java-based packages into Conda. What are the pitfalls with C and C++ programs? So what do I need to do? So we created this documentation, and we tried to build a community around that. And what we achieved in the last 1.5 years, so Bioconda is not older than that, we developed over 2,000 packages so far. I would say the most prominent software packages are all included, all the mappers, variant callers, We even have cheminformatic packages included, flow cytometry, natural language processing. So it's a diverse community which we try to grow. And so what you can see here is, for example, that we ask everyone to join kind of sub-communities, for example, an R or a Perl sub-community. So if people have problems getting their package or the package isn't compiling for whatever reasons, they can just ping the Bioconda -Perl community, and then there are a few guys that try to help to solve these problems. This entire project is completely community-driven and just lives from volunteers all over the world, actually, which contributes a significant of time to develop these packages and to kickstart them. I would say that the initial package to get that done can be tricky in the sense of it doesn't compile, or you need to patch the makefile to get it compiled. We all know these problems probably. But as soon as the first package is there, upgrading to a version is more or less 2 lines of code. So that's pretty easy, and we encourage everyone to participate. Just one remark to the community, because this is essential for the Bioconda and also for the Biocontainers community, is that it's really from all over the world, people are joining this effort. We have, in the last 1.5 years, we had over 200 contributors and 3,700 merge pull requests. This is huge for a scientific project that is so new. And what we also see is that actually upstream maintainers from packages joining us and contributing and updating their own packages. So, and this is actually what we want to achieve. So if we can convince upstream developers, so as soon as they release a new version, they also update the Conda package managers, their Conda package. I mean, this is the holy grail, right? So we want to encourage upstream developers to maintain their packages so that the entire community can profit. Okay, so that's Bioconda, and I think we did a pretty good job to develop this community and to drive that forward. But the new cool kid in town is containers, right? So all people are just talking about containers, and normal package managers are, at least I get the feeling, get sometimes unsexy. And containers have their advantages. So I do see, and we all do see, I think, probably a point in container technologies. And when I say the Conda packagement system can probably be 90% reproducible in all aspects up until the libc, containers can do more. So containers even can bind to a specific libc version and can shift the libc version and so on. So containers are there and containers will be used. What I wanted to, or what we wanted to prevent is that actually now all packages that we developed in various package managers get now just redone in Docker files or in other definitions how you can create containers. So what we did is we developed an approach that is actually a new approach of how to develop containers, which we called MALT, which is a layer donning approach to construct containers. So you don't need to write any Docker file. You more or less convert Bioconda packages to Docker containers. And this works in a very efficient way. So for example, if your CentOOLs binary is 10 megabytes, the resulting container which we will create with this MALT technique is 11 megabytes in size. So with this technique, we developed, or we integrated that in Bioconda. So as soon as you create now a pull request in Bioconda, Travis, the continuous integration service, which we need also to test our packages, will create a Docker container for you. And then we just talked to the BioContainers community, which did an awesome job in developing best practice guidelines, standardized ways of specifying metadata for containers and so on. And we asked them, hey, what do you think? Can we create containers automatically on the fly from Bioconda packages and create containers automatically for that? And they were really open to that idea. So we joined efforts here. We merged more or less both communities. And nowadays, as soon as you create a pull request to a Bioconda package manager or the Bioconda GitHub repository, and we merge those pull requests, merging means it has passed all our tests and we can build a container out of it. So as soon as we merge your pull request, you will get a Docker container for free. This sounds a little bit strange because this means if you want to have if you care about Docker containers, the preferred way which we advertise is to create a Conda package for us, because Conda packages are way more structured, are way more easy to define than Docker files, and you also get a Conda package for the entire community that wants to use Conda, and you get the container more or less for free, which you can then use. So this is a new technique where we try to join both communities and create efficient containers automatically without any human intervention. So BioContainers, on the other side, is defining standards, best practices for containers. You can approach them, talk to them, create an issue, I want to have this in this container, and they will respond, and then we will probably create a Conda package for it and create a container for it. They will develop, or they're developing training material, how to use Docker in production, how to integrate Docker in workflow environments. So this is all done by the BioContainers community. They develop great documentation, and they have also a website where more or less all metadata gets combined, also from the metadata which you defined in the Conda YAML file, and additional metadata. For example, we planned to bind this service also to the ELIXIR registry, so that the registry also consumes data for a specific software package, if for a specific software package there is enough material, and if there is a Conda package or a Docker container. So now we have Docker containers, but Docker containers are not the only container technology. For example, many people are using Singularity or Rockets because they believe that these container technologies are more secure than Docker, which probably is true. So they have a different choice. So what we do, and actually what is working is, so for every BioContainer, so for every Docker container, which we actually create automatically, we also create automatically a Rocket container. And we also create Singularity containers automatically for you. We cannot store them now because the Singularity registry is kind of in better status as far as I know. But essentially what we did here is, as soon as you give us a Bioconda recipe, this YAML file which I showed you previously, we can generate containers for Rocket, Singularity, BioContainers, everything for free. Even modules. So if you are used to modules on your HPC environment, there is now an interesting discussion in the Bioconda community how you can actually use modules automatically from Biocontainer technology, from Bioconda. And one crucial aspect for sustainability and reproducibility is that whatever technology you're using in the end, it's all the same binary. So it has the same compiler flags, it has the same bugs. We just repackage the same binary which we create with Conda. We just repackage that into different technologies. And you are now free to choose which technologies you prefer or which technologies is supported by your infrastructure. And you are ready to go. You get the same binary, and your pipelines should, at least at that point, reproducible. So who is using that? SnakeMage for example, is able to use Bioconda packages. It's working great. The Galaxy project is now also able to use Conda packages since a year. And Galaxy is also able to use the Docker containers, which we automatically generate. So essentially, as a Galaxy administrator, you can now decide, do you want to use Conda or Docker? As an administrator, you can just decide that, and then Galaxy will figure out if it downloads a container or a Conda package. I'm in contact with Cyrus, and they also using, at least they told me they are using these Biocontainers now. And one friend from Cyrus also told me that the Open Science Grid is using Biocontainers. So it's a little bit hard for us to know who is actually using it, because everything is completely free, no one needs to register, and we cannot track everything. But yeah, there are already a few users, heavily users, especially in the SnakeMake and Galaxy community, they're using it a lot. So with this, I just want to thank more or less the entire community. So, and that's kind of hard because it's so many people. But as a representative, I want to thank Yasset and Philippe from the Biocontainers community, and Johannes Köster and Ryan Dale from the Bioconda community. They are just awesome people that spend a lot of their work, which they are probably not paid for, and to drive this community project forward. I also would like to thank the ELIXIR project and the Dandy, especially Rolf Backofen, so my PI, for giving me the freedom to work on that as well. And I think we cannot appreciate that enough, that Travis on GitHub delivers an infrastructure for us today where we can do these kind of technologies nowadays for free.